Hello guys, welcome again to your world of physics. Now, having looked at the concept of energy in its totality, we are now moving on to another concept which has a direct link to energy, and that concept is power. Now, in this segment, we'll be looking at power and efficiency as a whole, and the objectives that will be covered here are 1. To define power and apply the definition, 2. To explain the term efficiency, and 3. To calculate the efficiency in given situations. So this will turn out to be a pretty short segment. So let us go ahead and explore objective number 1, which is to define power and apply the definition. Now, you would recall that we already established that energy is considered to be the ability to do work, and work is energy in motion. Now, the rate at which all this energy is transformed per unit time is called power. Or we could say that power is the rate of conversion of energy. And the unit for power would be watt or joules per second. And the formula for power as stated by the definition would therefore be energy over time. So energy over time, which is stated here, energy transformed per unit time, is known as the power. So to show the direct link between power and energy, let us go ahead and apply this equation to a question. So our problem is, what is the energy used by a motor of power 2.5 kilowatts, which is operated for 5 minutes? So we start with our original formula for power, which is energy over time. So if power equals energy over time, therefore energy would be power multiplied by time. And you're also being reminded here to work in standard units. So let us go ahead and do that now. So energy of this system here would be the power, which is 2.5 kilowatts, which would be 2.5 times 10 to the 3 watts, multiplied by the time in seconds, which given here in minutes would be 5 times 60, since 60 seconds make 1 minute. So that would be 5 times 60 seconds. This would give us a total energy of 750,000 joules. Or to show that you can manipulate your units, we could also write that as 750 kilojoules, or we could also write that as 0.75 megajoules. So here we see we can use our prefixes to make our answers look more scientific in value. Now, in reference back to the question here, we notice that we are dealing with an electric motor in operation, and in practice we know that the useful power output from a motor would not be equal to the power input. So we would actually have to account for some loss in power due to the fact that not all the energy used by the motor would go to good use, because some energy might be lost as heat from the friction of moving parts of the motor itself. So on that note, let us look at a term known as efficiency, which gives a relationship between the power output and the power input in terms of a percentage ratio of the two. So as was alluded to in the previous slide, we said that most machines, including the human body, are wasteful users of energy. So some energy is going to be lost. Efficiency is the measure of the machine's ability to maximize the energy input to produce useful energy output. So we can use the formula efficiency equals useful power output over power input times 100%. And as we said before, low efficiency is usually due to loss of energy due to heat produced from friction of moving parts, or heat loss due to fuel being burnt. Now let us look at an example. A crane lifts a 100 kilogram block of concrete through a vertical height of 20 meters in 25 seconds. The motor's power input is 1000 watts. Calculate the following, assuming G equals 10 newtons per kilogram and the pulley wheels waste no power. So here we want to calculate the useful power output of the motor and the efficiency of the motor. So let us see what formulas we need to apply here. Now we know that power is equal to energy over time, which is also equal to work done over time taken, because remember we showed a direct link between energy and work. So energy is the ability to do work, while work is simply energy in motion. So these two concepts are somewhat interchangeable. So in this question, if we find the work done to lift this concrete block, then we have the time taken, we can actually find the power. So we need to apply this formula, but we also need to apply work done equals force times distance moved. So these two formulas are necessary for part A. And for part B, we know that efficiency is given by this formula here, useful power output over power input times 100%. And in this formula, the percent is simply a unit. So it is useful power over power input times 100. And then you simply put your percentage as a unit of efficiency. So do not multiply by 100 over 100 as 100%. The percentage is simply a unit for your efficiency. So let us look at what our solution would bring for such a question. So for part A, where we're asked to find the useful power output, we begin by making recognition that G is 10 newtons per kilogram. Therefore, if the block is 100 kilograms, it means that the weight would therefore be 1000 newtons, because we know that weight equals mass times gravity. So this would be 100 kilograms times 10 newton per kilogram to give us a weight of 1000 newtons. Therefore, a force of 1000 newtons is needed to lift the block. Now, when this block is lifted, work is going to be done in terms of the force times distance, which is 1000 newtons times 20 meters, which gives us a work done of 20,000 joules. And since we established the formula that useful power output is equal to useful work done over time taken, then 20,000 joules divided by 25 seconds, which is the time taken, would give us 800 watts. So the effective or the useful power output is 800 watts. Now the efficiency, as stated here, is useful power output divided by power input. And remember, we will need to multiply this value by 100. So this would be 800 watts divided by 1000 watts, which gives us 0.8. And if we multiply that by 100, then that gives us an efficiency of 80. So that system would have an efficiency of 80%.